So here we see this formula that expresses the volatility of the portfolio as a sum of the marginal risk contributions. And here you see the expression for the volatility. So the volatility squared is this. Sum over all ING. These are fixed. Okay. So when you have to do the derivative of the, if you want to calculate the derivative of, say, let's do the derivative of sigma squared with respect to WIK. That is on the one hand 2, the derivative of this is wrong. 2, the derivative of this is not working. I have to. I'm going to use my whiteboard. I'm going to stop the share. I'm going to use the whiteboard. Something is not working today with my computer. I hope this works better. So sigma squared is the sum of Wi, Wj, and then the covariance, which is fixed. It's a number. That means that the derivative of sigma squared with respect to certain k is the sum of Wi sigma ik when I is not k plus 2 Wk sigma k squared. Okay, and this is the same as 2 sigma times the derivative of sigma with respect to Wk. Okay, so from here you can get the derivative of the volatility with respect to the weights from this expression here, divided by 2 sigma. That's perhaps the easiest way to do it. Is that clear? Is that clear? So can I get an answer, yes or no, if this is clear? I can give it in more detail, but this is maybe okay, you know. Can I get an answer? And these are things that you can calculate because this, you know, that you know, that you know, and this you know. Everything is known. This is known. More details? Okay. Let me give more details. Okay. So we saw here, let me see if this is understood. Let me see if this is understood. Is this clear? Let me ask that question. Let me start here. Is this clear? This is what I did in the previous slide. Is this clear? Yes or no? This is clear. Good. Okay. So if this is clear, let's look at the right hand side. The right hand side is here. If you look at the right hand side, what is this? It's a number. No. What is this? This is in the matrix. No. That's a number, and that's in the matrix too. So all of these things are things that you already know. Is the right hand side clear? Okay, it seems to be clear. Let's look at the left hand side. What is that? That's the volatility. The volatility is known, right? The volatility is known because it's the square root of WB W transpose. So it's a vector calculation. We know it's known. Is that clear? The volatility is known. If you can answer in the chat yes or no, then I see nothing on the chat. Does that mean that you don't understand? The volatility is the easy. No, you know, it's actually easy. Understand? Okay, good. How about that? That is unknown. That's the unknown part. But we know how to do that because everything else is known. You just need to calculate all of that and divide by that. Is this clear also? I don't have an answer. I will wait for an answer. So we have an expression where the right-hand side is known and the left-hand side has an unknown quantity that we can get by division. I still don't have an answer on the chat that this is known, this is understood. So, Zheng, can I ask you if you understand this? I don't have an answer. I don't. I think the chat is working, but I don't get any answers. Just yes or no. This is not hard. So that's why I want everybody to understand this. The assignment, when you finish, it's okay, it's understood. I guess Song said it's understood. Good. When you finish the assignment, you will see that it was not that hard. It just, you have to think in a different way. So, okay. So I hope that suffices. I'm going to okay, so I'm going to then continue with, I'm going to go back to the assignment. There's other things I want to say about the assignment. So you now know, everybody knows how to do the derivative. Everybody knows how to do the derivative. Now I'm going to share the actual assignment. I want to make a few more. So I'm going to now share different screen. I'm going to share my assignment. Okay. So in this assignment, what you need to do is we're creating an iteration. We're going to get the answer by iterating. We started with a guess, and the guess is the allocation with a zero correlation. And then you checked in the previous assignment that when you select that choice for the weights, then the these expressions that we have there are not equal to each other. They're different. Okay. So what I gave you is a method to iterate so that they all become the same eventually. And the method is you have the derivative. When you multiply by these quantities, you get a different ratio. So what we do is we define the next iteration to be precisely the one that will make the ratio to be the right thing. Okay. Note that if all of these numbers are the same, then they are equal to the volatility divided by 3. 3 because we have 3 assets that we're invested in. Okay, that's why the number 3 is here. So I'm choosing the weights that get me closer to getting this equation satisfied. So we start with a guess, we improve the guess, we improve the guess again, and eventually this will converge to the solution that we're looking for. That's the process that we are doing. This is a process which is very typical when you're doing calculations. It's called a fixed point theorem, or sorry, it's called a fixed point, and this is a fixed point iteration. There are theorems in mathematics that tell you that this method converges. Okay, here we don't need a theorem, we're just doing it in our computer. And this is something that you can do in Excel. You don't need a complicated program. Sorry, you don't need complex programming to be able to do this. Okay. So let me see if there are questions on this. I want to make sure this is well understood also. Is this clear? Is the process that you have to do clear? Zen says yes with your head. I think I can see you saying yes. Yeah. Okay. No questions? No questions? Okay. So it looks like everything is good. At least one person said it's okay. So, okay. So I'm going to stop that share, and I'm going to start a new one. So in the hour that we have left, what I'm going to do is I'm going to explain how we generate portfolio scenarios. Okay. So we saw last week how important it is to be able to generate scenarios, to be able to generate market scenarios, to be able to know what the markets are doing. And the way to do that is using statistics to generate possible situations for the market in the future. So I'm going to be sharing my screen. We're going to start by reviewing some topics in mathematics that will allow us to generate market conditions for the future. This method is called Montecarlo, and you may know Montecarlo is a code name. Let me explain by telling you why it's called Montecarlo. So Montecarlo is a name of a city in South France, which has a casino. Casino is where you gamble. Okay, and the idea of the casino is that it gives random outcomes. So when the United States was building the nuclear bomb, they used a lot of simulations when they were doing their calculations. The mathematicians and the physicists that were doing what's called the Manhattan Project. When they were doing simulations, they referred to the simulations with a code name Montecarlo, which has to do with a casino in southern France. This is the reason. Okay, so since then, Montecarlo has become a synonym of simulations. When we simulate, when we imagine what the market will be like future, then we use the name Monte Carlo. But Monte Carlo is really nothing but a a mathematical method to generate scenarios. That's what it is. And at the basis of this is something that we have already seen a month ago. And it's all based on probabilities and distributions. So this is the probability histogram. And this is the cumulative distribution function of a portfolio distribution. These things typically refer to a portfolio when we did it earlier, but in this instance, now that we're doing this is going to refer to the market. Our interest is in doing this for the market, for the portfolio. Both the market and the portfolio have a statistical distribution that could be given by a histogram or by a cumulative distribution function, CDF. Okay. And this is in one dimension. So here we have one variable. Here we have one variable. Okay, so on this situation, given a distribution that could come from either the history or could come from a model. Okay, the history is real. The model is theoretical. Okay, given this situation where we have either a historical method or a model, the question is, how can I generate markets? How can I generate variables that are consistent with this distribution? And the way to do that is this. I'm gonna post the question. So here's our question. This is our Montecarlo question. Given a data distribution with a probability density given by rho, this is given, can we produce a sample so that the values follow the distribution that we are given? That's the question, okay? Chat. Montecarlo is a city in the Principality of Monaco. You're absolutely right. It's in the southern part of France, okay? It's near the sea. So a question, this is an answer to, so Lee has a comment. Montecarlo is a city in the Principality of Monaco. Yes, and it is in the southern part of France. It's south of France. Good. All right, so, and there's a casino. It's very well known because gambling is allowed, and actually there's a very big casino. So here's my question. If I give you a distribution, how can you come up with a sample? See, this is interesting because in the past, what we have been doing is the opposite. What we had been doing in the past was given, in the past what we did is given some history, we produce rho. And what the Montecarlo method is going to do is going to be the opposite, is this. From rho, we get BXJ. Okay, so this is what we did. I'm going to choose a different color. This is what we did earlier. And this is Monte Carlo. Okay, so in the Monte Carlo, we're going back. The distribution is given, and we're trying to find this. I'll say this in a different way. In Monte Carlo, this is given. That's the unknown. And typically we want to do many of these. How many of these do we want to do? When you go to our question here, N is typically very large, typically millions. Okay, we want to generate many possible markets for the future. And the question I'm going to answer is this one. How do we do this? So the way to do this is this one. This is the answer. If f is the cumulative distribution function corresponding to the probability given to us, and I remind you, f prime equals rho, that's the relationship that we have between the cumulative distribution function and the density. And if these are uniformly distributed, I will mention how we can do this, but if these are uniformly distributed, then these are distributed like rho. So what you do, and this is the functional inverse of it. Okay? So what you do algorithmically is this. First, you generate uniform 0, 1 samples. And the computer can do this. The computers have functions that will generate uniform 0, 1 samples for you. Okay? That's the first thing. The second thing is you take the functional inverse of this generated uniform samples and then are distributed like rho. It's very simple. You just need to do two things. You generate random uniform samples, and then you apply then the inverse of the functional inverse of the cumulative distribution function. What you have is guaranteed to have the distribution that you're looking for. Rho. So this is simple, and this is very relevant because this allows the creation of possible future market conditions simulations. Okay, so simulations, we saw the relevance in risk management last week. We saw that we needed to simulate to be able to do, for example, value at risk calculations. We need simulations. Now we know how to do this, at least in one dimension. Today, what I want to do is I want to show you how to do this in higher dimensions and how to do this in a variety of different conditions. Okay, so before I go to higher dimensions, is this clear? Can you say in the chat if this is clear? Maybe you already knew it, but I want to make sure that all of this is understood. I am using a lot of mathematical formulations, so I want to make sure that everything that I'm saying here is understood. Can you tell me? Is this clear? I need this to be clear because I'm going to do it in higher dimensions now, and that's going to become more difficult. Okay, so Song says it's clear. Anybody else? Do I get a confirmation that it's clear? If it's not clear, say so. Okay, Peng says it's clear. Good. Okay, that's great. B, okay, Q, okay, perfect. Q, great. So then what I want to do is I'm going to ask the same question, but in more than one dimension. Okay, so I'm going to go to this question, except now we need the probability in higher dimensions, and well, we'll see how we have to do this because the same method is not going to work. We need to do something different. So when we go to higher dimensions, we'll go to the multivariate framework. Then there's two things that we need to know. So first, what is the density, which is now going to be a density of many different variables, and what is the cumulative distribution function? So we'll start with the cumulative distribution function, which is here. This is the cumulative distribution function. And it is the joint probability of my different random variables being less than or equal to given numbers. So these are the numbers here. So these are the numbers here. These are my variables. And as you can see, the variables become the terminal points for my sampling probability for my random variables. That's my cumulative distribution function. And then the density is obtained by taking the partial derivatives of the cumulative distribution function with respect to the underlying variables. Now, this is not something that we need to do particularly now. I know that I just told you how to calculate a certain derivative. We have another derivative again showing up. This is just a theoretical way of doing this. You're going to see that we can create algorithms that do these things for us. So this is the definition of the cumulative distribution function and the probability density in higher The cumulative distribution function typically looks like this. It used to be increasing. Now it's an increasing surface in the case of 2 variables. And in the case of more than 2 variables, it's not something we can visualize because it lives in a space of very high dimensions, but it still has this monotonicity. This function is monotone in each of its variables, okay? Monotone is increasing in each of its variables. That means that the derivative is positive. And this is what guarantees that this probability density is positive, as we expect, because it expresses a probability. Okay, so I hope this is clear. And if this is clear, to make sure that we understand what we're doing, I'm going to focus my discussion first on the Gaussian multivariate distribution. This is easier because it corresponds to the same case that we saw earlier, the same case as the Gaussian, except in this case now X is going to be a vector. That's what we're doing. Okay. So I assume you know this, but when it comes to Montecarlo, there are some considerations that I want to describe. Now, when we talk about any multivariate distribution, in particular the Gaussian, there are 2 important elements to the distribution. One is the distribution of the marginals, and the other is the dependent structure. So what are the marginals? When I have a distribution, I have each of these random variables could exist as an independent random variables, ignoring all the others. This is what gives rise to the marginals. So the marginals is the way we deal with each of the distributions individually. Okay. Or in other words, if you consider the distribution of each of those individually, what you can see here is each of these has its own probability density in dimension 1. So this is in 1 dimension, both of these in 1 dimension. That's the marginal. The marginals are not enough to determine the whole distribution, and this is where correlation comes into place. The dependent structure is what brings these marginals together. And we will see that we're going to be dealing with the marginals and the dependent structure separately. It's key to understand the multivariate structure, taking the marginals and the dependent structure separately. Now, again, the case of the Gaussian is particularly interesting, particularly easy, because we have formulas. So what I have here is the 2-dimensional Gaussian, which I know you have seen. I just want to write it, make sure that we all understand. And you would notice that I have written my the determinant of the variance covariance matrix using the correlation. That's how it's usually done. We don't need to do it that way. We don't need to do it that way. This thing that we have here is the determinant of the variance covariance matrix, happens to be that. And you know that the variance covariance matrix in the case of only two assets, the variance covariance matrix is sigma 1 squared, sigma 2 squared. And here you have is the correlation. So no, not two, not two. And then here, the correlation. And here the correlation. That's the variance covariance matrix. The determinant of this is that. Okay. And similarly, the exponent has this thing here, where these are the means of the marginal, the expectations of the marginal, and these are the marginal standard deviations. Okay. So in this case, the Gaussian is expressed very neatly using the marginal structure given by the mean and the standard deviation, and the dependent structure, which in our case is given by a single number. So the correlation is what determines the dependence structure. Dependence structure by correlation. This is significant. It means that if I go back there, in the case of the Gaussian, the dependence structure is exactly given by the correlation. The correlation is the only thing we need to determine the dependence structure. The only thing we need. We will see that in more general situations that is no longer the case, but at least in a two-dimensional Gaussian, that is the case. And typically we write the mean for all the marginals as a vector, and the variance covariance matrix is written like that. Okay, so this is in 2 dimensions. This is 2D. In K dimensions, in general, the expression for the Gaussian density is the same, but it's written in matricial form. So this is the matrix inverse of the variance covariance matrix. That's a vector, and that's a vector, and that's the transpose of that vector. We take the matrix and we'll multiply it by vectors to the right and to the left. And then we divide by 2k to the power k, where k is the dimension, then the determinant of that variance covariance matrix. So this is the Gaussian in higher dimensions. The Gaussian is going to be the basic element we're going to be using to doing our early portfolio transformations. Okay. Now, here is something that I hope you know. And if my distribution, if my multivariate distribution, my multivariate Gaussian is only for the Gaussian. If my multivariate Gaussian has uncorrelated marginals, then the variance covariance matrix is of a very special form. Okay, it has a diagonal, and then it has zeros outside of the diagonal. That's very convenient because in this case, the density of my Gaussians is the product of the one-dimensional densities. Okay, if you go here and rho is 0, then the exponentials that we have here break down into the product of the individual one-dimensional Gaussians. This is very convenient. And the reason is that when I have e to the minus x squared, this is e to the minus x1 squared minus x2 squared. And the exponential of a sum is the product of the exponentials. That's the reason. And that's why in this case, the product, so in this case, the density of my Gaussian breaks down as the product of the individual distributions. This is very convenient. It means that when we have uncorrelated marginals, the dependent structure is trivial. And in fact, the probability density is something that is very easy to deal with. Now, you may know that the you can always, I don't know if you know this, I'm going to ask you, but there is the theory of eigenvectors and eigenvalues that has as a consequence that I can always find a basis under which the matrix is going to be diagonal in this form. And this is what eigenvalues and eigenvalues and eigenvectors do for me. So here's, please answer in the chat if you know about eigenvalues and eigenvectors, if you have seen them before. I don't know how you call them. You probably call them something similar, but they are elements, vectors, and numbers that satisfy this equation for a given matrix. Can you answer yes or no if you have seen this before? In the chat, please say yes or no. Dai has seen it, says yes. Only one person said yes. Two people say yes. Three. Okay. Okay, more people say, okay, good. So that means that you have seen it. Great, very good. So if you have seen it, then I'm going to ask you a question. There's a mistake here. Can you tell me what the mistake is? What's the mistake there? What's the mistake? Who can see a mistake? Zero minus 1, 0. Yeah, exactly. So this is 0, that's minus 1, 0. You're right. 10, you're right. So let me ask you another question. What is the eigenvector for this matrix? What is the eigenvector? What is it? No, B is in 1, 0, 0. That's the one that I have here. This is not true because this multiplication is this. So this is not the case. It's a different one. It's a different vector. The eigenvalue is not 1, 0, 0 because there's a mistake. So let's ignore that. And now I'm going to ask you, what is it? What vector do I write here so that the vector, the same vector shows up here. Which one is it? What are the eigenvectors of this matrix that you have here? -1, 1, 0. No. No. Put -1, 1, 0 here. I'm going to multiply here. I'm going to get a 1 there. So it's not the same. And then the next one, I'm going to get 1. So it's not the same. It's not even a multiple. So no. Can you tell me what the eigenvalue is? I know that you told me that you have seen eigenvalues and eigenvectors, but I want to check how much you know about eigenvalues and eigenvectors. Most people have seen them theoretically, but they don't know how to work with them. And in this lecture, we need to work with them. We need to know them very well. That's why I'm asking. I want to know. Or maybe you saw and you forgot. Any other guess for the eigenvector and eigenvalue? No? No one knows, or you're looking for the answer? So maybe you don't know eigenvalues and eigenvectors very well. So how about 0, 0, 0, 1? Does that work? You see that? Yes, that works. So that's the eigenvector, and the eigenvalue is 1. Okay, so this is interesting because with the meaning of eigenvalues and eigenvectors, we can yeah. So with the value of eigenvalues and eigenvectors, we can get an idea what this matrix is. Who knows what this matrix is? This is the three-dimensional space. This matrix is a rotation of 90 degrees around the z-axis. The z-axis is the eigenvector 0, 0, 1. It's a rotation 90 degrees. That's what this matrix is. Okay, so the eigenvector is the direction that stays invariant, in this case, through a rotation. Okay, that's how you visualize eigenvalues and eigenvectors. For us, eigenvalues and eigenvectors are going to be different. They're going to have a different utility, which is that they will help us make the matrix trivial. When we change variables and express everything in the coordinate system given by eigenvalues and eigenvectors, then everything becomes very, very easy. And we can simulate, and as we will see, we can do many, many things. We can take very complicated markets and make them very simple. And we can take complicated portfolios and make them very simple. Now, in order to do that, I have some characteristics of eigenvalues and eigenvectors and matrices. There's a theorem that says that if A is a square symmetric matrix, for example, a covariance matrix, covariance matrix is square and symmetric, then you always have n eigenvalues and eigenvectors. Okay, so have n. These are eigenvalues and these are eigenvectors. And there is n of them. Note that if I go here to the previous example, do you know how many eigenvalues and eigenvectors this matrix has? This matrix is not symmetric. Okay, it's not symmetric. Therefore, what we're talking about does not apply to it. It's not a covariance matrix. And this matrix has only one real eigenvalue. Only one real. It has two complex eigenvalues. Complex eigenvalues are not going to be useful to us, but that's in this method of simulating markets. But it's okay because when my matrix is square and symmetric, I have all of them. I have n eigenvalues and eigenvectors, exactly like that. Okay. And the fact that my matrix is positive means that all my eigenvalues are positive. And there's another interesting feature, which is that the matrix that I can create by putting all of my eigenvectors as columns is orthogonal. Orthogonal means that the dot product of any two of these eigenvalues is equal to 1. I can normalize the eigenvalues so that this matrix is orthogonal. Right? It's orthogonal, meaning that the dot product of bk and bj is 0 when I'm looking at different vectors. So when I look at different vectors, these vectors are perpendicular to each other. Okay, so this is interesting because I can have a decomposition of my space. I can always have a decomposition of my space with a coordinate system, which is like that, orthogonal. And in that, my matrix is going to be diagonal. In other words, this is interesting because it says that what we saw here for the Gaussian distribution is something that I can always obtain. Yes, I can always obtain this if I change my basis. Okay, so this is always true. It's always the case when I choose as a basis the eigenvalues, the eigenvectors. Okay. And this is very important when we simulate markets, very important when we simulate markets. So there's other consequences, other features of eigenvalues and eigenvectors, which is that from the perspective of eigenvalues and eigenvectors, matrices become numbers. Eigenvalues and eigenvectors have another feature, which is that matrices become numbers. Okay, so I have examples. I can take the square root of a matrix, which is going to be a new matrix. The square root of a matrix is another matrix. And this matrix is expressed like that. A matrix is a transformation. And this is my transformation right here. I do it by taking the square root of the eigenvalues and keeping the matrix as is. You probably know that matrix A X is also this. Okay, so this is another way of writing my matrix. This is how my matrix will transform a generic vector X. It transforms the generic vector X by acting on each of its individual directions with the eigenvectors giving me the dilation in that part of the space and keeping the eigenvector direction constant. And this is just a component of my vector X into the direction of the eigenvector. I assume you know this. Let me ask in the chat if you know this. If you have seen this before, yes or no? The previous slide is something we will need. This we do not need for this course on portfolio construction, but this you need for other things. You need this, for example, for credit risk analysis and other things. So you have not seen this. Okay. Another thing you can do, you can take exponentials of matrices. You can also take exponentials of matrices. And the exponential of a matrix is another matrix where the eigenvectors are the same and the eigenvalues are the exponential of the previous eigenvectors. So this is how matrices become numbers. It's a very powerful concept. And all of this has a name, it's called spectral theory, which is something very important. We'll do something else, which is called big data. Do you know big data? Have you taken a course in data science, for example? Anybody has taken a course in data science? Well, I don't know. If you take a course in data science, these spectral methods become very useful. Okay. For us, we're not going to be doing data science in this course. We're going to be generating markets and creating future market conditions. And eigenvalues and eigenvectors will be useful to us because of that perspective, because of that analysis that they allow us to do to create useful Monte-Carlo simulations. Okay, there is an analogy that I'm going to get deeper into, and for that, I don't know. Let me ask you another question in the chat. Do you know music theory? Music. Do you know music theory? Anybody say yes or no? No? Okay, there is a connection between this and music theory. You don't know. Let me ask you another question. Do you know what an MP3 is? No? No? You don't know what an MP3 is? Yes. I don't know how you call that in Chinese, MP3. Yes. Yes. Okay. Good. So let me ask you a question. As you know, this is how your smartphone plays music. Yes. So this is an example of data science, which is very relevant for what we're doing today. Very relevant. So let me mention then an analogy, which is we have seen eigenvalues and eigenvectors for matrices, but there are other, these are infinite dimensional matrices. This is an operator, it's an infinite dimensional matrix. Think of it like a matrix with infinitely many rows and columns, okay? And it's the second derivative. It's called the wave operator. It's the one that tells us how waves propagate, like sound waves, for example, or light waves. And with this wave operator has very well known eigenvalues and eigenvectors, which in this case is the sine functions. The sine function is an eigenvector and an eigenvalue. The eigenvalue is n squared. And the sine functions are the ones that I have depicted here. These are the eigenvectors, although they're called eigenfunctions because they're also functions. And you may have seen that this is how you do music. So the MP3 technology, what it does is it takes music that you hear and then it digitizes music. it digitizes music using these eigenfunction decompositions. So another application of eigenvalues and eigenvectors is in the digitization of music. You can make music digital, and that's what MP3 does. It makes digital sound. There are analogies. If you were data scientists, you would see analogies between making music digital and Montecarlo simulation, which we're doing today. Creating or analyzing markets is the same as doing music digital. Okay, the same mathematics, just a different application. And I say this because it's relevant. At some point, I'll say more about music. What I want to do today is I just want to end with something to give you something to think about, and maybe allow me to give you an assignment about this. But maybe next week I will start talking a little bit about more of the relationships between Monte Carlo and music. So the basic conclusion of what we're discussing is that a covariance matrix will always be a certain diagonal matrix times an orthogonal matrix. This is the matrix of the eigenvalues, well, eigenvectors, sorry. And this is the matrix of the eigenvalues. So the diagonal has the eigenvalues right there. Eigenvalues. And the eigenvectors is what makes this orthogonal matrix. This is extremely important because it helps take a complex Gaussian distribution and we make it into a simple matrix decomposition. This will, when we try to do simulations here, this is hard, but making simulations here will be easy. Okay, this is hard, but this is easy. Remember what I told you earlier? If we take a uniform distribution and we map it with the inverse cumulative distribution function, I end up with a sample just like the distribution given to me. We're going to be able to do this in higher dimensions, but we need to be able to do it simply. We need to simplify the problem, and this decomposition is what allows us to simplify the problem. So a Gaussian distribution in high dimensions is always going to be a simple diagonal matrix with orthogonal matrices on both sides of the equation. Okay. In practical terms, there is another way of doing something similar, and it's called the Cholesky decomposition. The Cholesky decomposition is the following. I'm going to take my diagonal matrix, I'm going to take the square root of it, and I'm going to multiply it by my orthogonal matrix. The result is a matrix which has zeros below the diagonal, then it has a diagonal, and it has elements which are non-zero away from the diagonal. So this is what's called a triangular matrix. The Cholesky decomposition is H is a triangular matrix, which means it has zeros below the diagonal, or its transpose, which is also triangular, and this one has zeros above the diagonal. Now you have seen when you solve systems of linear equations that if your matrix, if the equation matrix is upper triangular or lower triangular, then it's very easy because you can solve your system by recursion. The same will happen when we're trying to do simulations. The same will happen when we try to do simulations. Okay. And you can do it with eigenvalues and eigenvectors as we did here, or you can do it with the Cholesky decomposition. The basic difference is this, that although this is very easy, when n is large, this is, I'm going to say, expensive. Expensive in terms of time, but the Cholesky decomposition is cheap in terms of time. This is hard to calculate. Expensive, it means that it takes a long time. Expensive, it means that it takes a long time. So it's expensive in terms of time, and cheap means that it's fast. Okay, so this is slow. This is fast. Now, computers these days are very fast, so this is less of an issue. But still, what will also happen is that when n is large, here we can have errors. And here, when n is large, we have less errors. Excuse me, okay? And moreover, you probably have seen methods to calculate eigenvalues and eigenvectors, and they're complicated. And this is going to be very easy. They're very easy implementations or very easy algorithms. Okay? And this is hard algorithms. So the Cholesky approach is better for many different reasons. It's cheaper, faster, and the algorithms are easier. And we achieve almost the same as we will achieve with eigenvalues and eigenvectors. Okay? Eigenvalues and eigenvectors they're useful for, say, MP3 or music digitization. These are not as useful for that, but these are good for simulations. Okay. Okay. So I have 5 minutes. Let me. The advantage of the Cholesky decomposition is that when I have my if I have my matrix and the Cholesky decomposition is already given to me, this, which is hard, okay, in very high dimensions, think of, for example, n equal 1,000, n equal 1,000 dimensions, this is hard. I can make it easy as follows. Okay, I have the theorem here. If I take a sample xi, which is Gaussian with 0 correlations, as we have here, and 1 standard deviations, then the Cholesky decomposition will map this Gaussian into my Gaussian with my variance covariance matrix H. You see, so the Cholesky decomposition maps a uncorrelated structure into a correlated structure. That's what the Cholesky decomposition does. Remember when we said that F inverse maps a uniform into my rho? We saw this earlier at the beginning of class. So this is how you deal with the marginals. This is the same, and this is how you deal with the dependent structure. This is how you deal with the dependent structure. It's exactly the same thing. This is always This is only for the Gaussian. This is Gaussian only. This is why this is so important. This is why Gaussians are so important. Because as we will see next week, the dependent structure for non-Gaussian is very difficult, but for Gaussians is very easy. And we have a very simple mapping done by the Cholesky decomposition that will take a independent uncorrelated Gaussian distribution into a correlated Gaussian distribution with a right correlation structure, the one that is given to us by H as the Cholesky decomposition of my matrix sigma. Okay. All right. So I think this is what I wanted to cover today. Maybe I'll do this. Well, I'll just walk you through how the Cholesky decomposition works. These are how the algorithms work. So given a matrix like that, the Cholesky decomposition, there are algorithms for that. I'm not going to go through the algorithm here, but I can tell you that the inverse of my matrix has another Cholesky decomposition, which is the same as the inverse of the Cholesky decomposition. And these are very easy to find out because the Cholesky decomposition is lower triangular, okay? So when I multiply my lower triangular by my upper triangular, I get my matrix A. That's the meaning of this. And they're very easy algos to calculate. And when I have my Cholesky decomposition, the way I transform my correlated space into the uncorrelated space is through the Cholesky decomposition. You have it right here. There's a lot of expressions, lots of formulas here. No need to go through all of that. I'll just tell you. I don't have time. I'll just tell you that the Cholesky decomposition is able to transform my Gaussian, multivariate Gaussian density into a very easy one-dimensional Gaussian. Okay. So for sampling, for generating scenarios, this is going to be very useful. We will see that next week. Okay. So I think I'm going to, yeah, exactly. All right, I'll say more things about eigenvalues and eigenvectors next week. Maybe I will describe the relationship between eigenvalues and eigenvectors and music also, some more, in case you know. I don't know, again, it looks like you don't know music theory. And then I will show you how we do simulations in high dimensions. Okay, that's what I will do next week. This will allow us to do risk management of portfolios under very generic market conditions, and will also allow us to create market conditions that have not existed before. Everything we have done in this course has been building from the past. With simulations, we can now create the future. Okay. We'll do that next week. I want to end by asking how you're all doing. How are the situation in Shanghai? I suspect many of you are in Shanghai. Everything's okay. You're doing fine. Yeah, no answer. Fine. It's fine. Okay. Very good. Okay, so then I wish you a very good weekend, and I will see you next Friday.